It's Chemistry Paper 1, May 2017. This question is about atomic structure. Write the full electronic configuration for each of the following species. Cl-, so first of all you've got to find out what the atomic number is, or the proton number, the number of protons and electrons in a Cl atom. So you'll find out that's 17 if you look it up in the periodic table, but the minus means that it's gained one more electron. A minus means it's gained an electron. So let's have a look at the 17 Cl. So it fits 1s2, 2s2, 2p6, 3s2, 3p5. Let's just check that. 2 add 2 is 4, add 6 is 10, add 2 is 12, add 5 is 17. So we've accounted for all 17 electrons. Let's just check again then. Cl is in group 7 of the periodic table, so it should have 7 electrons in its outer energy level. So in its outer energy level, the third energy level, it's got 2 in the S level and 5 in the P level. 2 add 5 is 7. It's got 7 in the third energy level from the nucleus, so it's in group 7. So that's correct. If it's a minus, then it's gained an electron, so it gains one more. Well, all of these orbitals are now full, so it needs to go into the 3p, so it becomes 3p6. Fe2+, let's have a look at the atomic number of Fe, which is 26, so it's going to fit 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6, or you could have the 3d6 before the 4s, but what you must understand is that if it loses 2 electrons, because it's become 2 plus 2 electrons, then they lose them from the 4s before they lose them from the 3d. So it becomes 1s2, 2s2, 2p6, 3s2, 3p6. It loses the s electrons before the 3d, so let's take the 2 electrons from the 4s, so it becomes 4s0, 3d6, or you can leave the s electrons out completely and just have it as 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Write an equation including state symbols to represent the process that occurs when the third ionization energy of manganese is measured. Well, first of all, manganese is Mn, and whenever you're talking about ionization energy, you've got to be talking about gaseous atoms. So we need the G symbol, state symbol, Mng, to show it's a gaseous atom. Its first ionization energy is when 1 mole of gaseous atoms loses 1 mole of electrons to make 1 mole of gaseous ions. So 1 mole, 1 Mn G goes to 1 Mn plus G plus an electron. I've lost 1 mole of electrons from 1 mole of gaseous manganese ions to make 1 mole of gaseous Mn plus ions. That's the first ionization energy. Second ionization energy is to do that again, but with 1 mole of Mn1 plus ions to make 1 mole of Mn2 plus ions plus 1 mole of electrons. And then the third ionization energy to do it again to remove the third electron. So 1 mole of Mn2 plus gaseous ions making 1 mole of Mn3 plus gaseous ions plus an electron. State which of the elements, magnesium and aluminium, has the lower first ionization energy. Explain your answer. Well, here I've got period 1, hydrogen, helium. Then I've got period 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then I've got period 3, so I've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Then I'm into period 4 with potassium and calcium. Now you'd expect them to go up across period 1, because as you go across a period you get more protons, so you get more nuclear attraction holding on to the electrons more tightly, and therefore a larger first ionization energy, and the atoms get smaller. And again you'd expect it to go up during period 2 as you get more and more and more protons across to neon, same amount of shielding, so more and more protons, more and more nuclear attraction for the electrons, and again across period 3 more and more protons as you go left to right across the period, same amount of shielding because same number of shells, and therefore you'd expect it to go up, and then so forth. However, there's a few anomalies. There seems to be a few anomalies. Let's have a look at period 3, because it's talking about magnesium and aluminium in period 3, but I could be talking about period 2. Let's have a look. It goes up to magnesium and then comes down to aluminium, and then it goes up to silicon, up to phosphorus, and slightly sort of down or across to sulfur. So why does it come down to aluminium? And it's because you've got 3s1, 3s2, and then you've got 3p1. So that's got, these have got s orbitals 3s1 and 3s2, and that's got 3s2, 3p1. So when you're talking about the first ionization energy from here, you're removing an electron from a 3s orbital, whereas here you're removing it from a 3p orbital. Now, a 3p orbital is further from the nucleus, and if it's further from the nucleus, there's less nuclear attraction, it's more easily removed. Your answer is aluminium, because the outer electron's in a 3p orbital, which is further from the nucleus, and therefore has a lower first ionization energy, because further away from the nucleus it's got a lower nuclear attraction. The sample of nickel was analysed in a time-of-flight mass spectrometer. The sample was ionised with electron impact ionisation. That means that you fire electrons from something called an electron gun. You bombard it with high-energy electrons, and it removes electrons from the atom. So what actually happens is nickel atoms would have other electrons fired at them via an electron gun, high energy electrons bombarding these atoms, and it would remove an electron from the nickel, so it becomes Ni1+. And that means that it's attracted down the mass spectrometer tube towards some plates that are charged minus, so it gets accelerated towards those, and then would hit the detector at the end when the Ni1+ ion then receives an electron and forms the atom Ni again, and in removing the electron from the plate, that generates a current, and the larger the current, then the greater the abundance, or the more common these atoms are. Mz means the mass of the atom divided by the charge. Well, let's assume that all the charges are 1+, so the mass divided by 1+ is just its mass. So we've got nickel atoms forming nickel ions, Ni1+ ions, and these are the masses, and these are the abundances, the amounts of each. So I've got nickel ions mass 58, so Ni1+ ions mass 58, and there's 61% of those. I've got Ni1+ ions mass 60 with 29.1% of those, and some Ni1+ ions mass 61, and there's only 9.9% of those. So let's imagine that there's 100% means, let's imagine we've got 100 of these ions. 61 of these ions out of the 100 have a mass of 58, 29.1 of the ions have a mass of 60, and 9.9 of the ions have a mass 61. So mass 58, we've got 61 of these. Mass 60, we've got 29.1 of those, and mass 61, we've got 9.9 of these out of 100%, or 100 of these ions. So imagine there's 100 particles, 58 of them have mass 61, so let's multiply those two together. So their combined mass is 61 multiplied by 58, 3538. I've got nickel ions mass 60, and I've got 29.1 of those, so 29.1 Ni+ ions have a mass of 60, so their combined mass is 29.1 multiplied by 61, 746, and I've got 9.9 Ni1+ ions mass 61, so multiply those two together, so their combined mass is 603.9. So if I add up the mass of all of these particles, the 3538 added to the 1746 added to the 603.9, end up with 5887.9. That's the mass of all of these atoms. I've got 100 atoms, that's what I decided at the beginning, so if I divide by 100, so the total mass divided by the number of particles gives me the average mass of a particle, 58.9. I've put it to 1 decimal place because these values are to 1 decimal place. So when it says, it says give your answer to 1 decimal place anyway. So I've given it to 1 decimal place to concur with these ones to make it similar to these ones here that I've got 1 decimal place. I've also, sorry, I need to backtrack here, give the symbol including the mass number of the ion which will reach the detector first in the sample. That's the lightest one, so the lightest one travels the fastest. They've all got the same kinetic energy, and having the same kinetic energy, the same amount of movement energy, kinetic energy, the lightest one goes the fastest. So that's 58 Ni1+. So it's got a mass of 58, it's Ni, it's nickel, it's 1+ because it's an ion, because it's been bombarded with high energy electrons from an electron gun so that it can be accelerated down the mass spectrometer tube, and also so that when it's 1+ and it hits the detector at the end and receives an electron back to form to turn the ion back into an atom, therefore it will generate a current which the larger the current will tell me the abundance, the larger the current, the larger the abundance, the amount that I have.